What is up, everybody? Make sure y'all can hear me. Make sure we're good to go. Let me know in the chat if you can hear me. Testing, testing, 1, 2, 3. Let me know if the music's too loud. All right. Yep, we sound good. All right, so we sound loud and clear. What's up, y'all? We're a couple minutes before 6 o'clock. We're gonna go ahead. Hey, what's going on, Ty? Let's see who we got here watching. Who's here? Who's here? Let's see. Let me see in the chat where you at, where you're watching from. Um, like I said, if the music is too loud, let me know. Um, all right, yeah, we sound so far. Sounds good. All right, so we're gonna jump right into it. So again, welcome everybody. It's Thursday. We are on day 2 of the Appsec Rabbit Hole. So today we are going to finish up the networking stuff that we worked on. Actually, you know what? I'm gonna turn the music down a little bit just because I think it's bothering me a little. All right. So yeah, we're gonna go ahead and jump into day 2 of Try Hack Me, our AppSec rabbit hole that we've been working on. Like I said, just let me know in the week. Let me know in the comments how your week's going. We're almost to Friday. I'm not gonna lie. Um, Mental health has been a little crazy. Everybody, fellas, ladies, everybody, always make sure you check on your mental health. It's been busy, but and because of that, I haven't really been able to take a step back and uh, handle a couple things. So it's been a little crazy. But this has always been my getaway. Gaming has always been my getaway. Hacking has always been my getaway. And my love for trying to teach and connect with people is always a getaway for me as well. So we're going to make that happen. Um, Again, if you want to leave anything in the chat, let me know how your week is going. Let me know where you're watching from. Let me know what you're interested in. Let me know how I can help you if you have any questions for me. Also, let's see. Um, let's just chop it up. Like I said, it doesn't have to be any topic. It doesn't have to be topic specific. It can be gaming, it can be cybersecurity, it can be whatever. As long as it's not anything that's going to get me canceled or demonetized before I can get monetized. All right. If you enjoy what you are watching, please like, follow, subscribe, tell a friend to tell a friend, share it. It is not mandatory, it's not required, but it is greatly appreciated. Also, or I don't think I did that. See, it's been a crazy week. I meant to set up my YouTube membership stuff this week, but I didn't get a chance to do it. But we will be doing YouTube memberships, and there will be little perks and stuff that's involved that comes with the YouTube memberships. I think we've decided what we'll probably end up doing is probably doing some of our in-depth hands-on stuff will probably be for the YouTube members, and then the AppSec Rabbit Hole stuff that we do on Try Hack Me and a couple other sites. We'll do that. Here on stream. Excuse me. Also, if you want to, you can leave super chats if you're watching on the Alpha Cybersecurity YouTube channel. We are streaming, by the way. We are streaming on like 5 different platforms. We are on Alpha Esports Technology, YouTube and Twitch. We are on Alpha Cybersecurity's YouTube and Twitch, and we are on my personal LinkedIn page. So, wherever you're watching, I appreciate you watching, and let's get to it. I just want to double check a couple things here. Making sure I'm not missing anything. So again, if anybody, thanks everybody who's watching right now. And I promise we're going to get to it in 1 second. I just want to make sure we are streaming everywhere where I said we're streaming. Let's see. Yep, Alpha Cybersecurity, LinkedIn. Yep, we are. We're in all of the places. All right, and I promise, like I said, if if we get through it enough today, we'll probably go and try to get some gaming in. Thoughts on the PJPT cert? Is that's the junior pen testing cert from Cyber Mentor, right? I'm gonna be honest with you. Cyber Mentor has done some really good work. They've brought on some really good and knowledgeable people in the pen testing and in the AppSec space. So the PNPT is a pretty solid cert. So based off of that and some of their other certs or some of their other trainings that they have, I don't see why the PJPT would be any different. So, like I said, I haven't seen the course material myself, but like I said, I've seen the PNPT stuff, and I've taken I think I've taken their web app and their mobile stuff, just because again, steel sharpens steel or iron sharpens iron. So, I took a look at it, and like I said, it's pretty solid. All right, so let's pick up where we left off the other day. We had finished up. We were in our network fundamentals, and we had finished up intro to LAN. So we have OSI model, packets and frames, extending your network, and then we got how the web works. So let's see how much we can get through. As you can see, like I said, I've already done it previously, but it doesn't hurt to refresh and it doesn't hurt to reteach or relearn. So that's what we're going to do. All right. So, like I said, just let me know wherever it is you're watching from, whatever, what you're into, what you're not into, whatever. Let's just chop it up. Okay. Again, it doesn't hurt to show some love. All right, so we are here. We like I said, so we started with what is networking. We talked about, just kind of give a quick recap. We talked about what networking is. So basically, networking is just connections. Networking can be people. Network can be technology. Networking can be friendships. Networking can be jobs. That's a network, right? And then we use Alice, Bob, and Jim and how they're all connected in that network, right? Then the internet is just basically a network of networks, right? The internet is one giant network that consists of many smaller networks. And then we did that really ugly. Actually, let me make sure I bring up Canva just in case I have to do another ugly whiteboard session. But we did the whiteboard session, kind of explaining the difference between public and private IP addressing and how that works. So, yep. So we got that going. Let's see. After we did that, we went into identifying devices on the network, and we talked about the IP address, how IPv4 is 4 octets, and each octet can go up to 0 to 255. But remember, 0 is the first number, so it's really 256 since zero is technically the first number. Okay, and then we talked about we talked about the public and private IP addressing. Then we talked about how basically the internet is running out of IPv4 addresses, so they started creating IPv6. And then we went into MAC addresses, so media access control addresses, and we talked about how they're split up. They're 12 characters, where the first half of the MAC address is usually vendor specific. That goes into so basically any Samsung device, or what it does is it looks at the like the network chip, or basically a small computer chip on that device, and that's what it does to identify it, right? So all Samsung devices, all Apple devices, from the manufacturer, will all have the same unique identifier, right? So all Samsung devices will have the same unique identifier for that first half, and then you'll have the unique address in the second half, right? So we talked about that. Let's see. Then we talked about the ICMP, which was the Internet Control Message Protocol, and what ping does, how ping basically searches the internet for live hosts. You can have ping, you can ping a different IP address, or you can ping a website. If the website has a connection, it will respond back, and you'll get these response packets here. Then we also talked about oh, okay. We did all of that. All right. So then we went into the intro to LAN room, and in the intro to LAN room, we talked about the LAN topologies. We talked about star bus and ring topologies. We talked about the difference between a router, a switch, and a hub. Usually, with the bus with these topologies, they're all on one. They're all sharing one line. So any requester will actually have to go through each of these. Whereas if you had something like a router or a switch, it would actually go to the device that it's intended to. A hub basically is just a dumb switch. It doesn't have the technology to allow the actual switching and routing that you would get from a switch. Let me see here. I'm just checking my Discord, making sure that we're all good here. All right, so we're good. All right, so once we talked about that, we talked about how most networks are set up. You have your internet here, so that's the outside. Remember the ugly whiteboard session. If you don't remember, please subscribe, follow the channel, and you can actually check out our Monday Appsec and Minecraft stream. We didn't get to Minecraft because we did start late, but we did go through this, and we talked about how the internet will connect. So the main line from the internet will connect to the router, and then your router will connect to your switches. Most people have a setup like this at home or at their office, because you don't have unless your router has like 16 to 32 ports. You're not going to be able to run Ethernet cables, right? So for example, in my home, I have a router that then connects to a switch that allows me to connect all my devices that I need connected via Ethernet. So my PCs, my consoles, my stuff for streaming, all of that is connected via Ethernet. And then things like my cell phone, my tablets, or whatever, that's connected via the Wi-Fi. And then any smart devices that I have, so uh, any smart devices that I have are connected on a separate network. We'll get into that later about why, just basically for security purposes. Actually, I'll just explain it quickly now. If you have a smart device like a fridge or a stove or a laundry machine or whatever the case may be, what tends to happen is the smart devices, even though they have smart in their name, they're not always updated like everything else is, right? So like how you might get a update on your computer every week, or an update on your tablet like sometimes twice a week. Smart devices don't update like that, and they can become very vulnerable. And if someone were to gain unauthorized access to your home through your smart device, then they could essentially navigate through the rest of the network. So how I have it set up, where okay, cool, you connect the Wi-Fi to that network. Congratulations, you have entered that said smart device, and then you can jump to the other smart device, but you won't be able to gain access to anything that has like any personal information, any personal data, or anything like that. And besides, most of that stuff is usually behind another password or some type of authentication. All right. It looks like we got some more people joining. So please go ahead and leave in the chat where you're watching from, what you're in, what's going on, how your week is going. How's your mental health, whatever. It doesn't have to be a super deep, in-depth conversation. I just want to make sure that you're good. You know what I'm saying? So, sometimes it helps. All right. So we went through all of that, and then we talked about subnetting. Subnetting is basically just, yeah, here we go. I thought we jumped up. Subnetting is basically the term given when you split up your network into smaller networks, right? So they gave the example of accounting, human resources, and finance. You have the internet, your router, your switches, but then what they do is they allocate a certain part of their network to different resources or different networks so that you can identify it. You can usually do this by IP addresses, setting up IP addresses. And then we talked about actually we're jumping ahead a little bit, but then we went into the ARP protocol, the address resolution protocol, and what that does is essentially gets the information of the MAC address that we talked about earlier, um, and try and it basically asks who has the MAC address, or who has the IP address, right? So the whole process goes here, right? So you have your MAC address and you have the destination MAC address, and then the message is, hey, who has this IP address? And then the IP address responds and says, oh, that's me. I'm this switch, or I'm this hub, or I'm this what not hub. I'm this switch, or I'm this other device. And then it says, okay, thank you. And it goes ahead and remembers it, right? And I said that's basically like when you get somebody's phone number or contact information for the first time. The first time you do it, you got to ask them, hey, what's your telephone number, or what's your email address, or whatever it is, right? What's your snap, right? As the young folks do. Um, but you have to input all that information, right? So you have to plug that information in, and you have to save that information. And then once you save that information, you can add it to your speed dial list. You can just push a button one time and it'll automatically call that number for you, or it'll automatically open up a message box for a message, so you can send your email or text messages or whatever. But that's essentially what's happening with ARP, right? ARP is saying, who has this IP address? The device responds and says, I do. And it says, thanks, cool. I'm going to make a note of that. I'm going to store it in my memory or my cache. Not CASH cache, but CACHE cache. Okay. Then we talked about DHCP. We talked about the difference between dynamic and static IP addresses. So just real quick, a static IP address is when you set the IP address, right? We talked about if you say that, hey, this is my name, or this is what I want you to call me, right? That is static. That does not change. I want you to call me this and only this. That's what you do with your IP address. You can set your IP address to be 192.168.1.10, and every time you reboot, every time you come online, every time you after every update, that computer will say, okay, I am 192.168.1.10. However, if you do a dynamic IP address, it uses what's known as DHCP, or the dynamic host configuration protocol. And basically what it does is, once you go online, it'll say what IP addresses or what names are available. And it'll say, okay, this is available. This is what you'll have. You have this for this set amount of time. Okay. 24 hours usually. All right. So that's usually what we do there. So now what we're going to do is we're going to go into the OSI model room. All right. Let's see. I've been working with this book, Bug Bounty Bootcamp, and learning how to do bug bounties. Also easing up on myself with the hacking, allowing myself to be good with mistakes and not knowing. Listen, and look, Ty, I keep saying it, man. Look, we all don't know everything, right? In my career, I've learned a lot, and I've forgot a lot, and I have to relearn a lot. And like I said, no one knows everything by default, right? I think the last stream, either last week or the week before, I showed what I use, right? If I'm pen testing an Active Directory environment, I have a mind map that I follow. If I'm testing a web application, I follow the OWASP web app testing checklist. APIs, I have something for that methodology as well. So it doesn't, so again, you don't worry about not knowing everything. No one knows everything, and no one should know everything, because again, you should have that balance. And bug bounties, like I said, yeah, bug bounties is a good way to kind of learn application security. Bug bounties is a good way to get into web application testing. However, I would just say with bug bounties, don't get discouraged if you don't find a lot of what is known as the low hanging fruit, right? So I know typically they'll tell you pick a vulnerability and just look for that, right? So some people say, okay, I'm just going to look for cross-site scripting, or I'm going to look for SQL injection, right? My thing was cross-site request forgery. right? And that was, that's what you look for. But what happens is over time, it gets, more and more people do bug bounties, and more people fix it. Companies get smarter and start fixing it ahead of time and patching it. So again, just look through it. I look at cats like John Strand and Dave Kennedy and get starstruck. I mean, like I said, you're gonna have some people who are really awesome. Those two guys are really awesome. John Strand, Dave Kennedy, John Hammond, Naham Sek. Sorry, jeez, wow, Naham Sek, um, Katie Paxton Fear, BSD Bandit. You got Tiberius. You got some really good and talented pen testers out there. And yeah, they're really good, or they excel in places that others don't. I'm not afraid to say that I believe a lot of them, actually probably all of them, are probably stronger pen testers than me currently. Like I said, especially with the fact that I've kind of been rusty. I think I've only had like one or two pen tests, maybe three pen tests in like the last 2 years. So whatever. But hey, that's again, that's why who they are, and again, it's good to aspire to be to that level, but at the same time, you also have to look at um, their experience. I mean, you have someone like Dave who's been doing this forever, from his time in the service and stuff like that. John Strand has been doing this for a very, very long time. Or you have people like who've come from, you know, uh, programming developer backgrounds. So again, nothing wrong with admiring and aspiring, but everybody has their own pace, and just stick to it. All right, so OSI model. So when you're talking about the OSI model, the OSI model is the Open Systems Interconnection model, and basically is just the model for networking. I believe it's, I mean, I think it's changed, but the OSI model still is, at its core, is still the same. So this basically just kind of dictates how all network devices are connected, and how they send, receive data, right? And the idea behind it is that there are 7 layers of the OSI model, and when dealing with technology or devices or whatever, the network connections or transactions um, touch each of these models, right? Each of these layers, I should say. And then so when dealing with the OSI model, we'll start from the bottom up, and then we'll go top down. So you have your physical layer, your data link layer, network, transport, session, presentation, and application, right? Um, for my networking folks, if this should pop up on a test like Network Plus or something like that, I always say a good way to do it is to kind of, remember. A good way to remember it is to create different analogies. Like when I was learning Network Plus, I did it from top down, and it was so all people seem to need data processing. That's how I remembered the 7 layers of the. That's how I still remember the 7 layers of the OSI model. All people seem to need data processing. So all application, people, presentation, scene, session, to transport, need, network, data link, processing, physical. Okay. Um, So let's start from the bottom up. So let's start from one with the physical layer, right? So the physical layer is basically exactly what it says. It's the physical components. So that is your Ethernet cable, right? That's it. That's your physical. That's the physical layer, right? Yeah, did it for Cisco. Yeah, no, it's that's the best way to do it, right? Um, so these it says devices use electrical signals to transfer data between each other in a binary system. So when talking about binary is just essentially ones and zeros, right? That's how all technology talks to each other. All computers talk to each other in the background using ones and zeros, and it's how the ones and zeros are grouped that make up the binary language. So then two is your data link layer. So data link layer focuses on the physical addressing of the transmission. So it's going to receive a packet from layer three, the network layer, which includes the IP address and then adds the physical address or the MAC address. Remember, so we talked about that MAC address and we talked about the IP address before. So it receives that information from the endpoint or the device that's receiving the data, and then everything that's inside it says blah blah blah. Slow down. Inside every network enabled computer is a NIC or a network interface card, and that comes with the MAC, a unique MAC address to identify it. So remember what I was saying. When they look at the MAC, they're usually looking at a chip or a NIC, and to determine that information about the how to identify it. MAC addresses are set by the manufacturer and literally burnt into the card. They can't be changed, so those are static. Although they can be spoofed, we talked about that as well. There are tools out there like MAC Changer that will allow you to try to spoof a MAC address if you're trying to trick a system. Okay, when information is sent across a network, it's actually the physical address that's used to identify exactly where to send the information. So again, when it says the physical address, it's talking about this MAC address. Okay, it's talking about that 12 character address that identifies the vendor and then the unique address of that device. Additionally, it's also the job of the data link layer to present the data in a format suitable for transmission. Okay. So now we move. So we have physical. So the physical is just like the physical components or the physical hardware, and then the data link layer focuses on the physical addressing. So that's the MAC address. So MAC addresses are basically considered data link layer two. Okay. Every MAC address or every device has a network interface card or a NIC, and that comes with a unique MAC address. So again, that's the data link layer. So now we're moving into the third layer, which is the networking layer, and it says this is where the magic of routing and reassembly of data takes place. While some of the protocols in this layer determine what is the optimal path that should be taken to reach the device, we should only know about their existence at this stage in the networking module. Briefly, the protocols include OSPF, or OSPF stands for Open Shortest Path First, and RIP stands for Routing Information Protocol. So those factors decide what route is taken and decide by the following. What's the shortest path? What's the least amount? So basically, what's the path of least resistance? Okay, the least amount of devices the packet needs to travel across. So if you have computer A and computer B, and it's going to say, do I need to go? Can I go a straight line because that would always be the quickest path? If not, then where's the fastest way I can get, right? So again, think of it as we want to get somewhere and we look up Google Maps and we try to determine the fastest path, the fastest time to get there, right? If I have to travel down to Atlanta, am I going to jump immediately on 85, or is there going to be traffic and require me to drive all the way down, some side roads, some side streets and back roads, or Peachtree Industrial? Can I drive Peachtree Industrial all the way down until I absolutely have to get on the highway? It's the same. It's the same process with networking. Okay. So again, it's going to look at what is the quickest path possible. And to do that, it uses two protocols known as OSPF and RIP. So OSPF is Open Shortest Path First. Open Shortest Path First, and RIP is the Routing Information Protocol. So it's going to use those two protocols to determine which is the fastest path possible. Okay. So now we go into the transport layer. So now transport layer is going into the protocols that are used when transmitting that data. So when talking about transmitting data, you have two protocols for that. There is TCP, which is the Transmission Control Protocol, and then you have UDP, which is user datagram. Yep, user datagram protocol. I always confuse the U. But when dealing with TCP, so let's back up a little bit. We talked about how most network stuff looks at the quickest path possible. Um, However, determining on the technology or what you need it for, it'll determine whether it needs to use TCP or UDP. So, for example, um, we're streaming right now. That is UDP protocol, right? So it's getting these packets from me, sending it across the internet to wherever you're watching me, right? If it drops a couple packets or whatever, that's fine. It'll pick up wherever it'll pick up wherever it picks up once it makes that connection again, right? TCP is more like if you're connecting to a website, right? So why the differences? Well, TCP uses what is known as a three-way handshake. So before TCP goes ahead and makes a connection, let's bring up our handy dandy ugly whiteboard. All right. So TCP, we have, let's just, I don't know, computer one, computer two, or whatever. Some network device one and network device two. So when you want to make that connection, what's going to happen is it's going to send something here that says, hey, I would like to connect, right? This is known as a SYN packet. So what happens is it says, hey, I would like to connect. Can we connect? And then the device is going to send something back that says, yes, we can. Now, this is known as, so I'm just going to say, so one is, oof, geez. So one is SYN, two is SYN ACK. So that's basically saying, okay, hey, I would like to, I'm making a request to connect. And this one is saying, I see and understand your request to connect. And yes, I am okay with connecting. Okay. And then the third step is known as the ACK. And what happens in the third step is now the device is saying, great, we are now connected. Okay. So that's known as the three-way handshake. It goes, hey, I'd like to connect. Can we connect? The second one says, yes, I think we can connect. We should connect. And then the third one says, great, we are now connected. So that's TCP, right? UDP, and we're just, whatever. Yes, it again looks sloppy. But UDP, you have device one and you have device two. And what's going to happen is device one is going to say, okay, so what you see, these little dots, these are network packets. So UDP is like, hey, sending this over your way, right? And device two is like, okay, yeah, I got it. But then what happens if some of these drop? So now you don't get everything. You get packet, drop, packet, drop, packet. There is no handshake. There is no connection. So because there's no handshake that basically established that connection, you're going to get the best effort. you're going to get whatever you can get. So where once you have the SYN, once you have this, once you have TCP, once you have that connection, it's basically making sure that the connection goes through securely. Everything gets transmitted the way it's supposed to. Everything gets transmitted in the order that it's supposed to. If for some reason it doesn't work, it will stop until it works again, and then you'll get it in the order it was received. Whereas UDP is like, hey, I'm throwing this to you, right? So think of UDP like, hey, catch. Did you get it? No. Okay. Did you get it? Yes. Did you get it? No. Did you get it? No. Did you get it? Yes. Right? It's best effort. Okay. So TCP makes sure it establishes a connection. UDP tries its best. That's the difference between TCP and UDP. Okay, so let's come back here. Best viewers on streamboo.com. Remove the space. No, thank you. I'm not going to do that. All right. So again, we talked about so let's summarize the advantages. The advantages of TCP guarantees the accuracy of data. The disadvantages of the TCP requires a reliable connection between the two devices. If one small chunk of data is not received, then the entire chunk can't be used, right? So again, think of it as, like I said, when you're, let's say you went to go watch this video, right? You missed a live stream, right? I hope you don't miss a live stream, but let's say you missed a live stream. When you missed a live stream, you're watching, okay, sorry, I was just looking at a message. So when you watch the live stream, let's say you're watching the live stream, and while you're watching the live stream, the internet goes out. Hold on. Okay. Stay focused. Okay. Okay. You're watching this stream after, right? So you're watching the stream, and when you go to watch the stream, your internet goes out. You're going to get that buffering, that circle, that whatever, or it's going to completely freeze up on you. That's because, but in the background, it's establishing that TCP connection. So it's establishing that connection to say, okay, yeah, everything is connected, you're good. But then when you lose the connection, it's like, well, everything stops until that connection is reestablished. Okay, so that entire chunk of data that gets passed through can't be used once the connection is lost. Okay. The other advantage is capable of synchronizing two devices to prevent each other from being flooded with data. Again, you're making that connection, and that connection is supposed to be secure. The disadvantage, a slow connection can bottleneck another device, as the connection will be reserved on the receiving computer the whole time. And then it performs a lot of processes for reliability, but TCP is slower than UDP because more work has to be done by using the devices in the protocol. So again, TCP is used for situations like file sharing, internet browsing, and sending an email. This usage is because the services require data to be accurate and complete, not having half a file, right? So again, this is where you're using TCP. So you're using TCP to send a file, right? So if you need to send a file or you need to send an email, that connection has to be established and secured before that data can get transmitted. Okay. Whereas UDP is a lot faster, but UDP doesn't care if the data is received. So remember what I was saying before, you get a packet, drop, packet, right? And they're actually using this perfect example, right? So TCP, you're making sure, hey, packet 1 is the head of the cat. I'm not gonna lie, it's kind of weird. Packet 2 is the body. Packet 3 is the bottom half. Packet 4 is a complete picture of the cat, and it when it gets sent over. Whereas UDP, you'll get packet 1, packet 2 got dropped somewhere, and then you get packet 3, so you don't get the whole thing. Again, they don't care. So again, I would say UDP gets used for things like um, streaming, like we're streaming right now, or voice over IP, where let's say that packet over you're making a phone call when you're on the phone, and then all of a sudden that connection goes out, and you're like, "Hey, I can't hear you. You're breaking up," right? That's similar to a VoIP call or whatever. And what's happening is those packets are getting dropped, so you can't hear it. And then once it does come back, or it does reconnect and make a successful connection again, you'll get the thing, right? So it'll be like, so the difference between TCP and U is that TCP is slower, but TCP has a connection, while UDP only focuses on. And if you get it, you got it. That's the difference. Okay. All right. So so that's your transport layer. Okay. So the name of the layer is transport. TCP stands for Transmission Control Protocol. UDP stands for User Datagram Protocol. What protocol guarantees the accuracy would be TCP. What protocol doesn't care if data is received or not by the other device? So that would be UDP. What protocol would an application like an email client use? That would be TCP. What protocol would an application that downloads files use? That would be TCP. What protocol would an application use that streams video? That would be UDP. See? All right, y'all. Yeah, thanks for watching, man. I hope you tune in, and if you haven't done so, go ahead and follow. All right. Let me know if you have any questions so far. If I'm moving too fast, or if you want me to kind of go back and touch on something, just let me know. Okay. All right. So with that, let's move into layer 5. So layer 5 is the session. So now the session layer is basically what happens once everything has been translated and formatted and it says once the data has been correctly translated or formatted from the presentation layer, the session layer will begin to create and maintain the connection to maintain the connection to other computer for which the data is destined. When a connection is established, the session is created. While this connection is active, so is the session. Session layer is also responsible for the closing of the connection if it hasn't been used in a while or lost. Additionally, a session can contain checkpoints where if the data is lost, only the newest pieces of data are required to be sent, saving the bandwidth. What is worthy of noting is that sessions are unique, meaning that data cannot travel over different sessions, but in fact, only across each session instead. All right. So again, the session layer is responsible for making sure the session is established, the session is going good, the session is active. If the session should go dead or the session kind of sits idle for a while, the session can cancel the session, or the session layer can cancel the session, or it can create like a checkpoint. So think of it like you're playing a game and you hit a save point. So you're playing the game and you lost a connection, or let's say you lost or you died or whatever, and now you come back to the most recent checkpoint. That's what's happening in this session layer. Okay. Presentation. So the layer 6 is the layer in which standardization starts to take place. You can develop any software such as email clients differently. The data still needs to be handled in the same way, no matter how the software works. This layer acts as a translator for data and to and from the application layer, data 7. Remember, there are 7 layers. The receiving computer will also understand the data sent to a computer in one format destined for another. For example, if you send an email, the other user may have sent the email client to you, but the contents of the email will still need to be displayed the same. So this is where things like encryption occur. So this is where they're making sure, the packets are being sent securely, it's being encrypted, it's being translated in a way where the other sessions, where the other layers can understand it and pick it up, where the other user, that if it's going between two destinations, the other destination will also be able to translate it, pick it up, decrypt it if it needs to be decrypted, because again, if you're using encryption, you should be using encryption. If you're sending packets over a website, that's all encrypted. So you're going from you to the web server or whatever, that's getting encrypted and then decrypted when it reaches there. So that's what's happening on the presentation layer. Okay. Then lastly, you have the application layer. So the application layer is the one that you're gonna know, because that's what you're looking at right now. Okay, so it says the application layer of the OSI model is the layer that you will be most familiar with. And this familiarity is because the application layer is the layer in which protocols and rules are in place to determine how the user should interact with the data being sent or received. Everyday applications like email clients, browsers, file servers, and browsing software such as FileZilla provide a friendly graphical user interface, or a GUI, and that's for users to interact with data that's sent or received. Other protocols like DNS, or the domain name system, which is how the website is addressed and translated into an IP address. So we're going to get into DNS in a little bit. Just think of DNS like the phone book for the internet. Sort of like how we talked about the MAC address, where it was like, hey, what device is using this IP address? And then it comes back and says, oh, that's me, and it records the physical address. DNS does that, but it does that for the domain name and the IP address. So, for example, when you go to Google.com, on the back end, what's happening is the internet is going to look at the system's going to look at it and go, what's the IP address, or what's the telephone number of Google.com? Okay, Google.com is this IP address. All right, cool. So that's essentially what it is. Like I said, it's like a contact list for the internet. All right. Okay, so now let's see. There's a practical game. Can you escape the OSI dungeon? Climb the levels in the correct order to escape the dungeon and reveal the flag. Can you beat our staff high score? Okay. So it says our hacker has been locked in the dungeon. Their only chance. No problem, Melissa. We're just going over some basic networking. Welcome. If you're new, please go ahead and give us a subscribe or a follow. If you have any questions, just leave it here. So what we're doing, Melissa, is we're just checking out. We're checking out TryHackMe's network fundamentals room. We just covered the OSI model, which is basically the framework of how network connections work on devices over the internet and things like that. All right, so what are we doing here? Okay. Okay, so we did physical. All people seem to need data processing. All people seem. Oh. All right, so that was wrong. Go back to the OSI lesson to confirm the correct steps. What did I do wrong? Physical. Oh, that's what I did wrong. Data link. I was doing it backwards. Network. All people seem to need. So transport. Session. Presentation. Application. Yay, we did it. All right. Says we completed it in 40 seconds. What's the record? 19 seconds. All right, well, whatever. Okay, so again, so that was just a little quick mini game. You know I'm gonna try it again, right? Really? Whatever. Okay, 20 seconds. Whatever. We did it. It's still close. All right. All right, so we can now move on to the next one for packet and frames. All right, so does anybody have any questions so far before we go ahead and move through it? Right. So again, if you want to watch it, if you're interested for the OSI model, I'll put it here in the chat. I believe the room is free. The Try Hackney membership has a free model or a paid model. You can get the paid model if you want to. However, again, there's nothing wrong with the free one either. There's a video here. It's about 20 minutes where they kind of go into it a little bit more. But I said, so just let me know if you have any questions. In the meantime, I'm going to jump into packets and frames. And we'll share this tab and we'll close these out so we don't have all these windows open. Again, so I'll put this one in the room too. So if you have any questions or you want to check out the room for yourself. All right. So, what are packets and frames? So let's just read what it says. Packets and frames are small pieces of data that, when forming together, make a larger piece of information or message. However, there are two different things in the OSI model. A frame is at layer 2, the data link layer, meaning there's no such information as the IP address. Because remember that you don't get the IP address until layer 3 layer 3, and then layer 4 you get it whether it's in TCP or UDP. I think I said that right. Think of this as putting an envelope within an envelope and sending it away. The first envelope will be the packet that you mail, but once it's open, the envelope still exists and contains the data. That's the frame. Okay. This process is called encapsulation, which we discussed in room 3, the OSI model. I don't remember that. But let's just go back and check real quick. All right, whatever. Let's not, because it's acting weird. Hold on 1 second, y'all. Hold on 1 second. All right. Sorry about that. Let's see. All right. We are. So, encapsulation at this stage, is safe to assume that when we are talking about anything IP address, we are talking about packets. When the encapsulating information is stripped away, we are talking about the frame itself. Okay. Packets are learn how to read. Packets are an efficient way of communicating data across network devices, such as those explained in task 1. Because this data is exchanged in small pieces, there is less chance of bottlenecking occurring across network larger than network across a network than large messages. Wait, what? There is less of a chance bottlenecking occurring across a network than large messages being sent at once. Okay, I'm sorry, that it just looked weird to me. I got dyslexic for a second. For example, when loading an image from a website, hey, appreciate it, Gucci, appreciate it. For example, when loading an image from a website, this image is not sent to your computer as a whole, but rather small pieces where it's reconstructed. So remember the cat we talked about. It sends it in different packets, and then you get the whole thing, and the final packet. Packets have different structures that are dependent upon the type of packet being sent. As we'll come to discuss, networking is full of standards and protocols that act as a set of rules of how the packet is handled once on a device. With billions of devices connected on the internet, things can quickly break down if there's no standardization. Okay, so we're talking about the different definitions. So when you see the time to live or a TTL, that is that's basically a timer. It's setting a timer for the packet to expire to make sure that it's not clogging up your network, right? So when we hear about let me not jump ahead. This field sets an expiry timer for the packet not to clog up your network if it never manages to reach the host or escape. So basically, what it's saying is, it's setting a timer where if it doesn't get the acknowledgement that the packet has been received, it's going to say, okay, this message will self-destruct, right, or something like that. So it's kind of like, okay, I send you a message. Let's say no one does this, and I don't recommend it, right? But let's say I send you a check in the mail, right? And it says you should receive the message. You should receive the letter within 2 to 3 days, right? But then on the third or fourth day, I'm like, hey, did you ever receive that? And they go, no. Okay, then I hurry up. I contact my bank, and I'm like, all right, I sent this check number 553, and the person never received it. I would like to cancel that check. So now what happens is now no one can take that check. Whoever stole the check can't take it and go cash it. It's the same concept, right? If it sends a packet and the packet never makes it to the destination, what it does is it wants to make sure that it removes it off of your computer before it clogs up your processing power on your computer. Okay. The checksum. The checksum is going to provide integrity checking on your TCP and IP address. If any data is changed, the data or the value will be different from what was expected, and therefore it shouldn't be trusted because it's corrupt, right? So let's go back to using the check example, right? If let's say I send a check and then I sign my name, but then somehow in between it going from me to you, someone else were to get it and they were to change the best viewers on streamboo.com, remove the space. No, thank you. But in the process of it going from me to you, someone else were to get it and they changed the price, the amount, or they changed the signature. Now, when you get it, you look at it and go, this isn't Davin's handwriting. This isn't Davin's signature. This is suspicious. That's basically what's happening with a checksum. It's checking the integrity. It's checking the integrity of the file. It's checking the integrity of the packet, right? So every time you send something, it has a checksum. It has basically a number assigned to it, right? Or a set of characters assigned to it, right? Whether this is not think of it. This is known as like the hash, right? So the hash can't be changed, right? So if I send a file over, the hash will be the same from when I send it to when you receive it, right? So if the hash is, let's say the hash is 120, right? But then when you receive it, it's not 120. Instead, it's 137. Now you look at it and go, wait a minute, it's supposed to be 120. Why is it 137? That's because it's been corrupted in some way. Therefore, it shouldn't be trusted. Okay. Source address. Your source address is the sender. right? And then a destination is the receiving IP address. So again, think of sending a letter. When you get a letter in the mail, you're going to get a letter from it's going to say from this person or this company, and it's going to have their name, address, city, state, zip code. And then when you send it to the person, on the center of the envelope is going to be name, address, city, state, zip code. That's basically what the source IP and the destination IP is. Source IP address is the IP address of of where it originated from, and the destination IP address is where it's going. So again, if we were to look at my IP address from where I'm sending this information to you, I would be the source. You're the destination. Okay. So now we jumped into the TCP, the three-way handshake. Now remember, we talked about this before. I remember my ugly drawing that I deleted. It was, hey, I'd like to connect. Then the other resource said, yes, sure, we can connect. And then it said, yes, we are now connected. Yay, everybody's happy. So it says the transmission control protocol is another one of these rules for networking. This protocol is very similar to the OSI model that we've previously discussed. The TCP/IP protocol consists of 4 layers, and is arguably just a summarized version of the OSI model. These are application, transport, internet, and network interface. So again, think of network interface as I'm not going to do that. Let's just read it. Very similar to how the OSI model works, information is added to each layer of the TCP model as the piece of data or packet traverses. As you may recall, this process is known as encapsulation, where the reverse of this process is decapsulation. The one defining feature of TCP is that it's connection based. So this is the three-way handshake that I was talking about, which means TCP must establish a connection between both the client and device acting as a server before any data is sent. Remember, hey, I'd like to connect. Okay, I know you like to connect. Let's connect. We are now connected. Now we can transmit data back and forth. Because of this, TCP guarantees that any data sent will be received on the other end. The process is named the three-way handshake, which is something we'll come on to discuss shortly. So again, we just talk about it again. So TCP guarantees the integrity. It does require a reliable connection. Otherwise, it has to be resent. Okay, so it's capable of syncing 2 devices, but a slow connection will bottleneck the other device. And then it performs a lot more processes to make sure that it's reliable, but it is slower than UDP. All right, so now when dealing with TCP packets, they contain a lot of different sections, and these are known as headers, right? So just like we talked about up here with the packets and frames, and then we talked about the source IP and the checksum and all of that, TCP has something similar. So TCP, the source port, we haven't talked about network ports just yet, but the source port would be the port where things come from. So TCP has 65,536 ports, right? That range anywhere from 0 to 65,535. But remember, 0 is a number, so 0 counts as 1. Therefore, it's 65,536 ports. And several of them have certain designations by default. So, for example, if you send an email, that's using a protocol called SMTP, and that is usually by default on port 25. If you're on a website, right, just like this right here, you're on Twitch, you're on YouTube, you're on LinkedIn, you're watching the stream. You're on a website. The website uses, depending on the version of the website you're on, uses 2 ports. There's port 80 for the web server, and then port 443 for the secure version of the web server. I'm pretty sure everybody here who's watching is watching this on port 443 because it's encrypted and it's secure. And you'll see that where if you actually look at the web address, you'll see HTTPS. If you see HTTPS, then you know that it is secure. If you see HTTP, then you're not, and that means any data that's being transmitted is being transmitted in plain text. Plain text is essentially exactly what it sounds like. You can read it, right? It's as plain and as clear as you hearing what I have to say. All right, so that's the source port, right? So the source port is the port of the sender, right? The destination port, same thing, is the port of where it's going. So again, I'm sending this information from me, or you're to Twitch, or you're watching this on whatever streaming platform. You're accessing this on port 80 or you're watching this on port 443. Okay. Then you have the source IP address, like I said before, my information because I'm the sender, and then or Twitch because Twitch is the sender where you're watching this, or YouTube wherever you're watching, and then the destination, you're the destination port. Okay. The sequence number. This is the piece of data. This data that's being transmitted is given a random number. Okay. The acknowledgement number is also the sequence number. So the sequence number is a number for the next piece of data that will have a sequence number of one that says we'll talk about it later. Checksum is the same thing. It's making sure that it's checking the integrity of the TCP integrity. It's checking to make sure, like I said before, that nothing has been changed, manipulated, or reprocessed, remanufactured, or whatever, or reproduced. A mathematical calculation, that's what we're talking when we talked about the hash before, is made where the output is remembered. When the receiving device performs a mathematical calculation, the data must be corrupt if the output is different from what was sent. So again, if I'm sending you something and my number is 120 and you look at it and it's like 121, 122, the data's corrupt. It's not, and it's going to get flagged. This header determines how the packet should be handled by either a device during the handshake process. Specific flags will determine specific behaviors. So remember, when we talked about the SYN, SYNAC, and ACK, those are known as flags. So the SYN message is the initial packet sent by the client and during the handshake. This packet is used to initiate the connection and synchronize the two devices together. So remember what I said. Hi, I'd like to connect. That's the SYN packet. Or the SYN flag. Then SYNAC is sent by the receiving device to acknowledge that the synchronization attempt from the client. So again, hi, I'd like to connect. Then you say, I acknowledge that you want to connect. I think we should connect too. Okay, so that's the SYNAC. And then the ACK comes back for me to say, yes, we are now connected. All right. The acknowledgement packet can be used by either the client or the server to acknowledge a series of messages and packets have been successfully received. Once a connection has been established, data is sent via the data flag or the data message. The FIN, this packet is used to cleanly close the connection. So once everything is done, we're saying, okay, we don't need to connect anymore. We're going to send a FIN flag or a FIN packet to say, let's finish our connection. Let's terminate our connection. And it's going to be a clean disconnect, right? So basically it's like this. And we say, we're good. You good? Yes, I'm good. All right, cool. Right? I feel like that's your FIN, right? And then you have a RST or a reset packet. That's what happens when the packet ends abruptly. So the communication has been terminated abruptly. This is the last resort that indicates that there was some type of problem. For example, if the service or application isn't working properly, or if the system has faults such as low resources. So remember how I said, all right, we're done here. Break. A reset is like, right? But it's like that, right? So there's a handshake and then all of a sudden it just stops, right? There's no clean break, right? So this is the connection being made and then it just stops, but it still thinks there's a connection. All right. Boy, I hope no one clips that. So again, they did a really good job of this diagram, way better than my ugly whiteboard attempt. But that's basically the three-way handshake. So SYN, SYNAC, ACK between Alice and Bob. All right. And now we talk about we're talking about the sequence number. So any sent data is given a random number sequence and is reconstructed using the number sequence and incrementing by one. Both computers must agree on the same number sequence in order for the data to be sent in the correct order. So remember, hey, here's my initial. So when I send you When I say, hey, I want to connect, I'm also giving you a number. So, hey, I want to connect. My number is 5, right? And then you go, okay, cool. Well, I acknowledge that, and here's my initial sequence number. Um, and I acknowledge it with the number, right? So you go, and then I acknowledge your SYNAC of 5,000, and here's some data that's my number plus 1, right? So you have your initial sequence number. So let's just use this one. So their initial sequence number is 0. Then when it got sent to the destination, it said, here's my initial sequence number, 5,000. And I acknowledge your sequence number of 0. And then when it gets back for the ACK, it goes, I acknowledge your initial sequence number of 5,000. And here's some data that's my initial sequence number plus 1. So then it was 0 plus 1. So now it's going to be 5,001, right? And now and it's going to keep going that way. Whew. All right. All right. So Alice and Bob communicate by reassembling the TCP handshake in order, the correct order in the static lab. Okay. So we're going to go ahead, enter the value of the flag given at the end. All right. So we're going to just open this up real quick. So, Sin, can you hear me, Bob? Synac, yes, I can hear you, Bob. Here, I can hear you. Ack, yes. Okay. Okay. And then we're gonna say data cheesecake is on sale. Ack, I hear you. Then we're gonna say Finn, I'm okay. Yep, me too. Okay, bye. Did I move too fast there? I'm gonna close it and I'll reopen it and just kind of do it again. So again, we're creating a connection. We're passing data and then we're cleanly breaking the connection. So remember, send. Can you hear me, Bob? Bob says, yes, I can hear you. So that was the send act, and now act, okay, great. You heard me. Now after you do that, hey, now that you heard me and now that we're connected, cheesecake is on sale. That's the data packet. Okay? And now they receive that and they acknowledge it. Oh, cool, cheesecake, I hear you. Right? And now Alice says, okay, well, that was all I needed to say to you. We can terminate the connection. So I'm all done. He says, yep, I'm done too. And then, okay, goodbye. So now that's basically how the network package gets transmitted. Okay. All right. So let's close this out. All right. UDP. So again, we talked about the UDP before. UDP is user datagram protocol. UDP is stateless, which means it doesn't try to make a connection like TCP, which is stateful. It doesn't require a constant connection. It basically does best effort. So if it drops a packet here and there, it's like, hey, that's your own problem. Okay. We talked about TCP. UDP is faster than TCP, but it does not care if the data is received. UDP leaves the application to decide if there's any control or how the packets are sent. But the disadvantage is quite flexible to software developers in the sense UDP does not reserve a continuous connection like TCP. And then it goes, this means that unstable connections result in terrible experiences for the user. Okay. So again, time to live, TTL. Again, same thing, expiry time for the packet so it doesn't clog up even if it doesn't manage to reach the host. The source address, same thing, same source IP address, destination address, source port, destination port, and then the data. Okay, so now here you have Bob and Alice. Bob is like, I'm sending a request. Alice is like, cool, here. Right? So it's kind of, there is no back and forth of a constant connection. It's you get what you get. Okay. Whew. All right. So now ports. So remember we talked about ports. We talked about ports have different programs or protocols on them by default. And they usually have a standard rule or a standard port. Now the ports, just because they're standard does not mean they can't be changed. These are just what the ports are by default. Okay. So, for example, the file transfer protocol, which is used by file sharing applications, which means you can kind of download from a central location, right? So that's like if I have, let's say I go, hey, go to my website to download my latest ebook, right? That kind of can be considered a file transfer protocol, but I'm just giving you an example, right? But that's what FTP is. FTP is a client server. It follows the client server model, and you can download it from a central location. Okay, that's usually on port 21. Port 22 is secure shell. So this is if you to securely log into systems via some type of interface, right? So for my Linux users, I'm pretty sure you're already familiar with SSH is, but let's say you wanted to connect to the command prompt somewhere else. That would usually, but you want to do it securely. That would be secure shell. That would be an SSH connection, right? If you've ever used an application called Putty to connect to a device remotely, that's SSH. That's a secure shell. Okay. Port 80. Remember, I was telling you about port 80 and port 443 being used for World Wide web servers, websites, web applications. That's what you're looking at on your browser, and then 443 is the same thing as port 80, but it's using a secure encryption during the connection. Then you have 445, which is your server message block. This is usually for also for transferring files. So similar to FTP, but it also allows you to share devices like printers, right? So if you ever had a shared printer, like let's say you work in an office or even at home, you know everybody connects to the same printer. They're able to connect to the same printer. They might be using the SMB service or server message block. And then you have RDP on port 3389. Now that's similar to SSH, but that's if you're actually using the graphical version, right? So if you go and let's say you remote into your computer at home, right? Or you're at work and you need to connect to your computer at home, or you're at home and you need to connect to your computer at work, and you need to connect and see all the applications, resources, everything on the desktop. So you're using the graphical user interface, or GUI, which is basically like your screen, like your desktop. That's using the remote desktop protocol. Okay. All right. So it says open the site attached to this task. Where's the task? Okay, over here. So now it's saying use port 8.8.8.8.8. What was the port? Port was 1234. Okay. So basically what just happened here was we connected to IP address 8.8.8.8, and we connected to port 1234 to see if there was what service was running on there. And it did connect. There was a connection that was received, and it was just a flag. Okay. All right. So let's just close this up. All right. So now it says let's go ahead and extend your network. All right. So I want to make sure we finish. I want to make sure we finish all or at least try to finish all the networking today. Let me see where we are. Yep. So this will be the last one, and then it goes into how the web works. So we'll go ahead and finish this one, and like I said, it'll be a short stream. What is about 90 minutes? All right. So let's go ahead and let's go into the extending your network room. We'll share this tab. So port forwarding. So now we're going to talk about port forwarding. We're going to talk about firewalls. We're going to talk about VPNs, LAN networking devices, and then we're going to do a simulator. So port forwarding. Port forwarding is an essential component in connecting applications and services to the internet. Without port forwarding, applications and services such as web servers are only available to devices within the same direct network. Take the network below as an example. With this network, the server has an IP address of 192.168.1.10 that's running a web server on port 80, where the only the two other computers on this network will be able to access it, right? Okay, so that's because, so what you're doing here is you have your router. So remember, again, if you want, you can look at it, look at the video from the other day. But remember, once you connect to the router and you're connected internally from the external, from the public internet, you'll get a private IP address like this. So now everything that is connected can connect to this because it's all on the same internal network. However, if you needed to share this with the internet, you would do what is known as port forwarding, so that you're basically opening up a port to let someone from the public internet get into your private internet, private IP address. Obviously, there's dangers around it. Actually, if you saw when I set up my net Minecraft server a couple weeks ago, we talked about why I was going to use a service versus setting up port forwarding. But let's just move on with this. So, all right. So only the other two computers on this network will be able to access it. This is known as the intranet, right? Because this is all internal. So this is all internal. There's no outside. There's no outside resources or outside interference. This is all internal. You have your internal IP address on port 80. The web server's on port 80. This internal IP address, and now everything can connect to it internally via the router. If the administrator wanted the website to be accessible to the public, like I said, using the internet, they would have to implement port forwarding like the diagram below. So here you have the same internal network, right? But you want to make it access the net. You want to make it access the public internet, right? So again, this is my Minecraft server, right? So this is my Minecraft server. So everybody at Alpha Esports and Technology, if they want to, can connect to my Minecraft server. But now let's say my room at one of the community centers, my esports room in one of the community centers, wants to connect to it. What I would do is I would open up a port to give it access via the internet. Okay, so basically what would happen is I would say, okay, cool, let's open up a port, and this is the IP address, right? And now here's the other gaming center, or here's the community center that we want to do our connection to. So now they're going to connect from their public IP address to the internet and connect to my IP address, my public IP address on port 80, which is then going to go through my router and connect to my Minecraft server. Got it? So let's see. Okay, so with this diagram or this design, Network 2 will now be able to access the web server running on Network 1 using the public IP address of 82.61.51.70. So that's this one right here. It's easy to confuse port forwarding with the behaviors of a firewall, a technology we'll discuss later. However, at this stage, just understanding that port forwarding opens specific ports. Remember how packets work. In comparison, firewalls determine if traffic can travel across these ports, even if they're open by port forwarding. All right. Port forwarding is configured at the router of a network. So remember, my Minecraft server, my second location that needs to connect to my Minecraft server. I'm going to go to this router. I'm going to go to this router here and say, open up port forwarding on this IP, and it's going to give me this external IP address. So remember, this is my internal IP address. This is my external IP address, and this is coming from the internet. So the internet says, from here, this is your IP address. Whether when you connect to inside your building or your house or Alpha Esports Technology, this is your internal IP address. Okay. Now I have my community center over here, and I'm like, I need to connect here. So I opened up port forwarding, and I know this IP address. So now all I have to do is say, hey, go to 82.62.51.70 on port 80. And it's going to go, okay, through the internet. This is my IP address through the internet. And it's going to go, okay, we know this because this is the public IP address of Alpha Esports and Technology. And it's going to go through the router. And the router is going to say, yep, I did allow public access. So it's going to go through the router, and then it's going to connect here. Now, when we talk about firewalls, the firewall will have a rule in place that's like, are you allowing this? I don't know. Should we allow this? And it could possibly block it even if you have it open. Okay. All right. So firewalls. A firewall is a device within a network that's responsible for determining what traffic is allowed to enter and exit. So think of a firewall as border security for a network, right? So firewall, think of a firewall as a club bouncer. Are you supposed to be here? Let me check your ID. Okay. Yep, you're allowed to be here. You're granted access. You're not allowed to be here. Nope. I'm going to deny you access. Okay. An administrator can configure a firewall to permit or deny traffic from entering or exiting a network based on numerous factors, such as where's the traffic coming from? Where's the traffic going? What port is the traffic for? And what protocol is the traffic using? Now, going back to my Minecraft example. Let's say someone from an IP address that I don't trust or I don't allow is trying to access it. What the firewall is going to do is go. So let's just see if we come back over here for port forwarding, right? So usually a firewall is going to be here or here, right? So it's going to come through here. And the firewall is going to go, whoa. Who are you and what do you want to access? And it's like, hey, I'm 172, I'm 68, 4321, and I want to access the firewall. I want to access the Minecraft server. Firewall is going to look at it and go, well, I can't. You're from a location, or your IP address was flagged as something that I need to deny. Sorry, you can't access it. Meanwhile, let's say someone from 172.68.50.21 shows up and says, hey, firewall goes, whoa, who are you? Hey, I'm 172.68.50.21. Firewall checks the list and goes, oh, nope, you're good. You can access the Minecraft server. So that's what's happening here. Okay? So when dealing with firewalls, there's a bunch of different categories for firewalls. You have a stateful firewall or a stateless firewall. So the stateful firewall is going to use all the information from the connection rather than just looking for a specific packet. The firewall is going to determine the behavior based on the entire connection. So it's going to look at the whole picture. It's going to look at it and go, wait, who are you? What are you here from? How'd you connect? It's going to basically going to ask you 21 questions before letting you access it, right? Now it does require a lot of resources compared to a stateless firewall, but again, if it's from a bad location, it's going to block everything. Okay, whereas a stateless firewall uses a specific static set of rules to determine whether or not the packets are acceptable. So, for example, a device sending a bad packet will not necessarily mean that the entire device is blocked. So these firewalls don't use a lot of resources compared to the stateful firewalls, and it says they're much dumber. So it says, for example, these firewalls are not only effective as the rule. These firewalls are only effective as the rules that are defined within them. If a rule is not exactly matched, it is effectively useless. So that's like saying, um, let's say I go using that IP address example where I say, hey, you know what? 172. Hold on, y'all. Oh, jeez. Sorry. Okay. So right here it says 172, 168. I mean 172, 68, 43, 21. Right. Let's say that came from. Let's say it came from a specific device, right? That had that IP address, right? It's where a stateful firewall will look at that and go, not only is this IP address blocked, this device is blocked. Stateless will go, okay, well, you blocked me because of this IP address, but what if I change this IP address? And then a stateless firewall might let it go through. Okay, so however, the firewalls are great when receiving large amounts of traffic from a set of hosts, like like a distributed denial of service attack. Okay. Let me see. Firewalls come in all shapes and sizes. Dedicated ports can handle magnitude. Software such as Snort firewalls can be categorized into 2 to 5 categories. Okay. Says what layers of the OSI model do firewalls operate at? That would be layer 3 and layer 4. I just want to double check something real quick, even though it doesn't. Does it not? No, I don't think it gives you. Oh, that's a practical stop. Okay. What category firewall inspects the entire connection? That would be a stateful, and then individual packets are stateless. All right. So now let's go ahead and open up this site here. It says malicious traffic are marked as the packets in red. The legitimate traffic are packets in green. The protocol you need to block is port 80. Configure the firewall to prevent the malicious packets from reaching the web server 203.0.110.1. Okay, so the website 203.0.110.1 is under attack. Quickly add some firewall rules to stop the server from crashing. The packets in red are from the attacker's machine. Okay, so we need to block the source IP of 198.134, destination of this one, and it's coming off of port 80. We're going to drop add rule, and now we're going to block everything. Okay, so I mean, it kind of moved kind of fast, so we're actually going to let it. We're actually going to let essentially what was happening was distributed denial of service attack, right? So we'll let it do the simulation real quick. This is sending legitimate traffic. However, we need to block the malicious traffic without stopping the legitimate traffic from reaching. So we need to protect our router by building a firewall rule that will say we cannot allow 198.51.134 to send anything to port 80, but we're gonna but 203 is fine. Okay, so let's restart the simulation. So the source IP address is 198.51.134. The destination IP address is 203.0.110, and then it's on port 80, and we want to drop. So now when we go ahead and do that, you'll see everything stops here. Basically, imagine a firewall is here at the router. Imagine the firewall was right here. So that's basically what was happening. It was like, nope, you can't pass. There's a rule here that says you can't pass. Okay. All right. VPNs. So virtual private network is allows you to connect to devices on separate networks, or Yes, it allows you to make connections on separate networks securely by creating what's known as a tunnel. Okay, the devices that are connected are they make their own private network. So remember when we talk about public the public IP address versus the private IP address, or the public network versus the private network. When you connect to a VPN, it's a virtual private network, and what happens is it creates a tunnel. So let's go to our handy dandy ugly whiteboard. Come over here. So we have a device here, right? And then we have a device here. Now remember, we need to create a secure connection. So we can't just go here because straw magnifying glass. Right? If someone were to be watching or monitoring the network, they could see this information, right? They'll be able to see what's happening, whatever data is being passed over this network, right? Cool. So when you create a VPN, what happens is so when you create a VPN, it's going to create a tunnel, right? So right? So now when the data gets passed, you can't see what's going on here, right? You're not able to see it because it's going through the tunnel. So now, if we use that magnifying glass again, that's an ugly magnifying glass. But if you try to use the magnifying glass again, magnifying glass can't see what's happening. What's going on, Maddox? Long time, brother. Right? So it's being blocked. You can't see that because it's going through this secure tunnel. So that's essentially what happens with a VPN. Okay? So virtual private network is you're trying to make a connection to another device or network securely, and it's being encrypted is through this tunnel so that you can't see what's happening. Okay? So that is, I think that's the second or third time we used our ugly whiteboard connection. But hey, as long as it's helping people understand. All right, so devices connected within the tunnel form their own private network. For example, only devices within the same network, such as within a business, can directly communicate. However, a VPN allows two offices to be connected. Let's take the diagram below to see the three networks. So here you have your internet connection. So here's network one, here's network two, and then network three is these little blue ones connected right here, and they're connected over the VPN. These are devices that are connected to the network over the VPN. Okay. So, I mean, it's connected to the router, yeah, but like I said, I would probably, yeah, whatever. It's fine. But like I said, it's connected and it's using that tunnel that we drew earlier. All right. So again, it allows networks in different locations to be connected. So again, um, once upon a time, long ago, we used to have what was called as remote work. Right? I'm joking, right? Because I mean, there are getting a lot of companies are getting rid of remote work, but um, you know, a lot of remote workers might connect via VPN to their networks. Um, if you as a pen tester, right? Sometimes we have to do a pen test on a network, but we can't be there in person. So what they do is they grant us access through a VPN. So we connect to the VPN, whether it's an application or whatever, and we connect securely to their network, which allows us to then do what we need to do for our penetration test. That's essentially a VPN. Okay. It also offers anonymity. Whatever. I can't say it. I can't say it right now, but it offers privacy because again, you can use the VPN to safely report where freedom of speech is controlled. Again, using that secure tunnel, your traffic can't be viewed by other people. Um, Usually, like I said, your internet service provider can see your traffic, but and because of that, it can be tracked. But instead, VPNs offer that secure tunnel, which doesn't allow you to access it unless you're connected to it. Okay. It says Try Hack Me uses a VPN to connect you to our vulnerable machines without making them directly accessible on the internet. Again, using my Minecraft server example, the Minecraft server that we built, we're connecting to that Minecraft server essentially over a VPN because I don't want to open up port forwarding to give anybody access to my actual internal network. So what they do is they connect to this site that creates a tunnel to my Minecraft server securely, and that's how we are doing our online Minecraft clubs. All right. We're almost done. We're gonna wrap this up, and then we got these. We got the LAN networking devices, and then we're gonna call it, and then we're gonna jump into how the web works on Monday. All right. So VPN technology has improved over the years. Let's explore some of the existing VPNs. So PPP VPNs. This technology is used by PPTP to allow for authentication and provide. I'm so immature and provide encryption of data. Your VPNs work by using a private key and a public certificate, similar to SSH. A private key and certificate must match for you to connect. This technology is not capable of leaving a network by itself, meaning it's non-routable. Okay, so PPTP is point-to-point tunneling protocol, and that's the technology that allows data from PPP to travel and leave a network. Okay, point-to-point tunneling protocol is very easy to set up. And then you have IPsec, which encrypts data using the IP framework. IPsec is difficult to set up in comparison to the others. However, when it's successful, it has the strongest encryption out of all of them. Okay. So you want to usually, if you can, you usually want to do a IPsec VPN. Oh, I don't know if we did it say restream. Maddox, that was Ty that was saying what's up. I think you sent it to the actual bot. All right. So we have that. So let's get into the LAN network devices. I feel like it was repeating itself again, but hey. So we talked about the router before. So the router's job is to connect the networks and pass data between them, and it uses this by by a process called routing. Routing is the label given to the process of data traveling across networks. Routing involves creating a path between networks so that this data can be successfully delivered. Routers operate on layer 3. So remember, physical data link. Now level 3 is network, right? All people seem to need data processing. So routers operate on the network layer of the OSI model. They often feature an interactive interface such as a website or a console. So remember, if you ever have an issue with your router and they're like, "Hey, go to 10.0.10.1 or 192.168.1.1." Man, I want to play more. I'll probably do that when I get home. But that's where you connect to your router. Routers are dedicated devices and do not perform the same thing as switches. Okay, so you see, computer A is connecting via several routers to computer B. So they're connected, but they're connected because of all the different routers. We can see computers A network is connected to the network of computer B by two routers in the middle. The question is, what path will be taken? Remember, we talked about the open OSPF, so open shortest path first. So, what it would look at is which one is the most reliable and which one has the fastest medium or the fastest path, right? So it's going to look at is this a fiber optic network versus a copper network? Is it, whatever, and it's going to determine based on that which way it wants to go. So let's say this way is fiber and this way is, but up here is copper. Is going to look at it and go, okay, so what's the shortest path possible? They're about the same. Okay, cool. Which one is faster and which one is more reliable? Oh, this is fiber. Cool. I'm gonna go to fiber route. Okay. All right. So a switch is a dedicated networking device that's responsible for providing means of connecting multiple devices. So remember what I said before when I said at home, I have several devices that are connected via Ethernet because I just prefer Ethernet over the wireless, especially for the things that I have to do between my streaming, my pen testing, all of that. I just need that strong connection. So because of that, I have a couple switches in my house that will connect from the router and allow me to connect to multiple devices via Ethernet. And I only save and I use my Wi-Fi for my wireless devices. All right. Switches can operate both on layer 2 or layer 3. However, these are exclusive in the sense that layer 2 switches cannot operate on at layer 3. Okay? So they're either a layer 2 or a layer 3. They can't be both. For example, a layer 2 switch in a layer 2 switch in the diagram below. These switches will forward frames. Remember, these are no longer packets as IP protocol has been stripped onto the connected devices using their MAC addresses. Now, I will say I'm not the strongest when it comes to networking. So, but so if they say it's a layer 2 switch, then I'm going to go with it. So you have your router that's connected from the internet, and it's going to connect to the layer 2 switch. And then from that layer 2 switch, it looks like 1, 2, 3, 4, 5, 6, 7, 8. So 9 devices are connected via Ethernet to this layer 2 switch. Switches are solely responsible for sending frames to the correct device, right? So let's say you get something that needs to connect all the way down here. Remember what we talked about before with the different networking, with the different network types. So you had your star topology, your star topology, ring topology, all of that. And then you had things that were called hubs. Those are called like dumb switches because they don't have the technology in it. So if that were to be that, then it would try to go through every single part before it could find you. Whereas the switch, it would go, hey, we need to connect to number 8. We need to connect to the device number 8. It's going to go, okay, cool. Hey, device number 8, right here, right? As opposed to going, are you device number 8? Crap. Are you device number 8? Are you device number 8? Are you okay? You know what I'm saying? So there you go. Now let's move to layer 3 switches. These switches are more sophisticated as they can perform some of the responsibilities of a router. Namely, these switches will send frames to devices like layer 2, but they'll also route packets to other devices using the IP protocol. So let's take a look at the diagram of a layer 3 switch in action. So the technology is called a VLAN, or a virtual local area network, which allows specific devices within a network to be virtually split up. This split means that they can all benefit from things such as an internet connection, but are treated separately. This network separation provides security because it means that the rules in place. All right, go ahead, Maddox. All right, thanks for tuning in, man. It means, yeah, you could, okay, yeah. So basically, here's how it's separated with the VLANs, right? So you have a VLAN here. So if you look, 192.168.1.1 and 192.168.2.1. So these are two separate networks, but they're on the same layer 3 switch, which means now they connected a VLAN. So now it thinks these are two separate networks, even though they're on the same device and it's on the same router. It's split up like it's two separate networks. So it's been configured to say all these devices are on one VLAN and all these devices are on this VLAN, and they are completely separate from each other. Even though they're on the same device, even though they're using the same router, they are completely separate from each other because they are on separate virtual local area networks. Okay? So the sales department and accounting department will be able to access the internet, but they will not be able to communicate with each other. So technically, they don't know the other one exists. That's what happens with VLANs, right? So I want to, so like for example, I have a VLAN for my for my gaming PCs for my esports stuff, right? That allows me to have its own that so now they so that VLAN has its own network. It does not worry about anything else that's going on. It's off to its own network, doing its own thing, communicating with only those over there. Okay. All right. So now let's do this networking simulator. All right. So what are the instructions? Deploy the static site attached to the task and experiment with the network simulator. The simulator will break down every step of a packet. Every step a packet needs to get from point A to point B. Try sending a TCP packet from computer 1 to computer 3 to reveal the flag. So from computer 1 to computer 3, and then we're going to send the flag, and then we're going to do this. So we'll just say hello, and we're going to send the packet. All right, so we're going to let it go through the process, and then we're just going to check the log. Actually, we'll probably do it again just so we can kind of pay attention to whatever. Okay. So let's see what happened here. Probably can't read it. But basically, it started the TCP handshake from computer 1 to computer 3. So it said, hey, so I went through here to here, and said, hey, I want to connect. Okay. The router says, hey, computer 3 is not on your local network. So because it's not there, we're going to send it through the router. And then it sent the ARP request. So remember the ARP request, it was like, hey, who's on computer 3? Can you let me know who's on computer 3? And computer 3 said, I'm computer 3. And it let the router know. Router said, great. I'm going to cache that information, and I'm going to now go back to computer 1. So now computer 1 says, hey, I want to connect to computer 3. Router goes, oh, I know who computer 3 is, and it's going to establish that connection. Okay. So now once it established that connection, it sent the SYN ACK, and then it sent the ACK, and now that connection has been made. So then once that connection has been made, it's going to send a TCP packet, which was the data, which was the hello. So I said hello. I said, all right, cool. I received it. And then once that was done, it terminated it, right? So now let's try computer 3 to computer 2. So now let's send a packet from computer 3 to computer 2. So you see it's going to try to send the handshake, and then the router is going to go, wait, who is computer 2? Computer 2 goes, I'm computer 2. Computer 2 goes, great. Computer 3 wants to talk to you. Computer 2 goes, okay, I acknowledge it. Computer 3 goes, I acknowledge that it wants to talk to me. Computer 3 goes, I acknowledge the connection. And now that we're connected, I am going to send you the data that I needed to send you. And then computer 2 goes, I received it, send it back, and then they terminated the connection. Okay? So now let's go from computer 1 to computer 2. We're just going to send it UDP. So now what happened there is it said, hey, Computer 1 said, who's computer 2? Router said, hey, who's computer 2? Computer 2 said, I'm computer 2. Router said, okay, cool. Hey, that's computer 2. And then the computer 1 said, all right, cool. And sent it straight to computer 2. Now, I'm just curious to see if it'll ever fail. Oh, now that it knows that who computer 2 is, you'll see. Now that it established it, you can send it all the time, right? Because the router cached that information. Right. So now you can see there's no longer an ARP request because it's cached in the router. All right. So okay, so we got everything. All right. So how many handshake entries are there in the network log? Well, we did a lot more, so we don't need it, but we already answered that question. All right. So I think with that, we are now done with networking fundamentals. Yep. We are now done with networking fundamentals. So since we are now done with networking fundamentals, all we have to do from here, all we have to do, sorry, what did we say? Was it pre-security? All right, so we did networking fundamentals. So we completed that. We already completed that. So now we're going to go into how the web works, but we're going to save that for Monday. Okay? So we're going to do how the web works on Monday, and then we'll do Linux fundamentals. We'll probably, depending on how fast we get through, um, how the web works, we'll do Linux fundamentals. But I'm thinking we'll probably do Linux fundamentals on Thursday. I'm kind of liking the pace. Like I said, we probably knock it out in 2 hours this way. Not, people aren't, whatever. And then, like I said, and then also if we get done quicker, then like I said, we can get to some Minecraft. All right, but then after that, after we have Linux fundamentals, where we're gonna learn the basics of Linux, and then after we learn the basics of Linux, I'm thinking we actually might check out Over the Wire, just so you can understand the Linux a little bit better. And then after you do that, there's Windows fundamentals. So we'll learn about the UAC, control panel, NTFS. We'll learn about that. All right. So, like I said, it's been about 2 hours. It is almost 8 o'clock. I'm gonna close up shop. I mean, again, I want to get some gaming, but hey, at least we got to play a little bit of gaming with Try Hack Me. So if you guys like this, again, please share it. Where if you haven't done so already, please like it, subscribe, follow wherever you're watching, and and just let people know that we're doing this. Trying to get more people involved and get people into to get some education and to learn more about cybersecurity and networking and stuff like that. And again, we're doing a lot of this. We're doing a lot of this using free platforms, so it doesn't cost you anything. And just again, it's not necessary, but please follow, subscribe, so to let us know that we're doing the right thing here. All right. So I'm gonna go ahead. I'm gonna close up. Get home, get me some dinner because I actually have a doctor's appointment in the morning, and I need to fast. So I'm gonna make sure I eat now. So y'all go ahead. Y'all be safe, and I will talk to you all on Monday. I may stream tomorrow if I can. My Fortnite team has a match. So I'll probably stream that. If not, I'll definitely stream after to kind of let you guys know what happened with the match, and I'll probably stream something after. probably get some gaming in after. Let's see what happens. I don't know. Fingers crossed. This guy got a lot going on. All right. But y'all be safe and take it easy. Peace out.